Alright, let's see here. We've got another trig substitution integral. It is the integral, the fraction numerator, square root of y squared minus 25, denominator y cubed, that's dy. These are in terms of y, so everything looks nice. We don't have to worry about getting confused. So let's see here. We have variable minus number under the square root, so this is kind of the same example that we did earlier if we're going in order. So it's the same type. Let's do two things here. One, let's go ahead and label everything. In this case, the x in our places will be considered. Are you writing? You were writing and not telling me. Okay, the x's are taking the place of y's, and the a is taking the place of 5, because that's 5 squared. Okay, and with that, let's just go ahead and draw ourselves the triangle that we have over here. Right triangle. We can put our angle wherever we want, as long as it's not the right angle. So our hypotenuse is y, our adjacent is 5, and our opposite is y squared minus 25. Okay, and we can build all those things, but having the template already laid out for us gives us a little bit more confidence and keeps us from having to think as hard. So while we've got this stuff in here, what do we need to replace? We need to replace this square root. So down here we see that that square root is going to be replaced with a tangent, which is 5 tangent. So the square root of y squared minus 25 we'll replace with 5 tangent of theta. And then we also have a y cubed, and y would be the same thing as x over here. So we can say that y equals a secant, that'll be 5 secant. And then our dy has got to go to d theta somehow. So that'll be a secant tangent. So that's 5 secant theta tangent theta d theta. So let's make some of our substitutions here. So let's take it over to thetas. Get out of these y's. So our fraction. Up top we'll replace this with the square root with 5 tangent of theta. So let me just kind of keep my colors going here. There's where all the substitutions are coming from. I know I highlighted that. The next thing we will have will be the y cubed on the bottom. Y is 5 secant, so that's going to be 5 secant quantity cubed. 5 cubed is 125. Well, yeah. And secant cubed. Whatever that might mean. Let's pick a different color to kind of show where that comes from. So since we're writing in blue, let's use yellow. So this comes from here, 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 here. And then we have our differential. We're replacing dy with 5 secant theta tangent theta d theta. Alright, let's find a happy color. I don't know what's going on there. Orange is going to get some love here. So I've got other things written down in the template, but they're just really kind of helping us get to where we're going. They might not be necessary to write down if you can get everything organized. So let's see here. What do we have? We have 1 secant on top and 3 secants on the bottom. We have 2 5s on top, 1 5 on the bottom. I think we'll just kind of clean this up a little bit. So 25 on top, 125 on the bottom. That'll put 5 on the bottom. Looks like there'll be a tangent squared on top. And a secant will cancel out to leave a secant squared on the bottom, d theta. Looks like we could use a little bit of trig magic here. So let's see here. Let's pull the 1/5 out to the side. And let's see, tangent squared. Tangent squared, I'm just guessing what I need to do here is sine squared over cosine squared. And then secant squared on the bottom. Let's see if we want to do this. We can do it as secant's the same thing as 1 over cosine, so it'll be 1 over cosine squared. There's possibly different approaches to this, but in that case, those cosine squareds cancel out, and what we're left to integrate here is 1/5 sine squared theta d theta. So this is going to get a little bit more fun than some of the rest of them, but let's see here. So we know that with the trig powers, the sine squares, sine cubes, whatever, we have the power reducing functions where we try to integrate. So that's what happened for us before. So let's see, 1/5 times, and we can rewrite sine squared as 1/2 minus 1/2 cosine of double the angle, d theta. Let's move me, and then we can write over here and go back if we need to. So let's see here. Kind of clean that up before we do the actual integration. So integration of 1/10 minus 1/10 cosine of 2 theta d theta. All right, we're ready to integrate that. It's not going to be that bad. Something interesting will happen, so we want to stay on our toes here. So let's see here. If we integrate that, it will be 1/10 theta. And if we integrate cosine, it goes to sine. So we're going to have, if you do the u substitution, minus 1/20 sine of 2 theta and plus c. Now we have something that hasn't occurred before. So we need to get this thing back to y. And some things are easy to do, and some things we're going to have to draw on some outside information. So we can change the theta back to y because we can use any inverse trig function from our triangle up here. But what we've done in the past, when we use the triangle to get rid of a trig function, like sine of theta or something like that, we had this angle in here. So notice that now we're trying to find the sine of twice an angle, but our triangle was centered around a certain angle. Well, we do have relationships for that. So this is a trig identity that you will need. It should have showed up in trigonometry class. But sine of 2 theta is the same thing as 2 sine theta cosine theta. So we're going to use that. Okay, and then we have the angle that's in our triangle, sine and cosine. Okay, so just let me write it. Maybe I'm in the way now. Come on, me. We'll have to go back up and down to reach our formula. But let's see here. So we're going to have 1/10 theta minus 1 over 20 times 2 sine theta cosine theta plus c. So let's kind of go back and grab the things that put this in the terms we want. So we're going to have 1/10, and then we need something to represent theta in terms of y. So I think looking at my triangle up here, inverse sine would be a good choice because, inverse cosine. Because cosine is adjacent over hypotenuse, so that means I don't have to use the square root part. So I'm going to use inverse cosine of 5 over y. So cosine inverse 5 over y. Okay, then minus 1 over 20 times 2, so that's minus basically 1/10. And then sine, if I go back up here, Sine would be my opposite over hypotenuse. So it's my square root over y. So let's see that. So that's the square root of y squared minus 25 over y. And that's times cosine. Well, cosine was 5 over y. And then plus c. So we've got this thing back in terms of y. We are done. We have integrated it. So we have our function. I'm going to clean it up a little bit. 1/10 cosine inverse of 5 over y minus, and there'll be a 5 over 10, so that's 1/2. We'll have the square root of y squared minus 25 on top and a y squared on bottom, but note that those y squareds aren't really interacting, plus c. And in this process, there might be a couple of different avenues you could take, but your answer should be somewhat numerically equivalent to this. Should be able to reconcile. The main thing that came out of this that we haven't seen in any other ones is that in the integration, which was fairly common with the trig powers, if we had a cosine cubed or cosine to the 4th, sine to the 4th, something like that, we used an identity. Let me come back here, color we didn't use. We used this identity right here when we reduced some powers, but it changed the angle. And our triangle was centered around theta. Okay? So our sometimes things move great, sometimes they don't. There's a little bit of lag here. Now we're too far. All right, yeah. So our triangle was centered around the angle theta, but in changing that angle so that we could actually integrate it possibly, we have a new angle. So we had to use some type of identity, which some of these double angle identities are pretty good for reducing that. I'll introduce the rest of those if needed in other examples. Thank you.